All right, you guys, if I sound a little tired at this point, it's because I've made this recording a few times, but it's going to be good this time. So, reactions in aqueous solutions. Chapter 4 in your textbook, this is a picture of the Brown and LeMay textbook, which is the one that I use for a lot of my presentations. But today we're going to talk about precipitation reactions specifically. So, before we can do that, we need to review a little bit about solutions. Remember, a solution is a mixture. It's a homogeneous mixture of two or more pure substances, which means that they're uniformly distributed. So when you look at a solution, you can't necessarily tell that you have two different substances mixed together. The solvent is the substance that's present in the larger amount or in greater abundance, and the solute or solutes, if there's more than one, are the substances dissolved into the solvent and usually present in smaller amounts. When water is the solvent, those substances are called aqueous solutions, and AQ is the symbol in a chemical equation for those types of solutions. Anything that can dissolve in water could be the solute, like soluble ionic compounds, aqueous acids, soluble bases, and molecular compounds that are polar. So water, remember, is a polar molecule. So it is a molecule. It's covalently bonded the hydrogen to the oxygen. But the oxygen wins the battle for electrons, so they're pulled slightly towards the oxygen end of the molecule, giving it that partial negative charge. The hydrogen end has a partial positive charge, and so every hydrogen from one water molecule is attracted to the oxygen excuse me, on the next molecule. So there's a hydrogen bond between water molecules, and that attraction is what causes a lot of water's properties. So when you have a polar solvent like water, it's going to dissolve other polar solutes like alcohols and sugars, and it'll also dissolve soluble ionic compounds like sodium chloride. If you have a nonpolar solvent like hexane, and remember this is nonpolar because carbon and hydrogen have very similar electronegativities, so the bonds are all kind of equally distributed with electrons. Those types of solvents will dissolve nonpolar solutes like oils, gasolines, grease, and other nonpolar compounds. So take a look at this list, 4 different substances, and decide what, if any, will dissolve in water, and give a quick explanation as to why, and do that right on your summary sheet. It's important to note that when ionic compounds are dissolved in water, they dissolve into their separate ions. So in this case, sodium chloride, purple being the sodium ion, the sodium ion gets surrounded by the oxygen end of the water molecules and pulled apart, and the chloride ion, the green here, gets surrounded by the positive end of the water molecules and gets pulled apart. So in solution, this compound actually exists as separate ions. It's called dissociation, and it's important to remember that with ionic compounds. Any compound that will dissolve into ions or dissociates into ions when it dissolves is called an electrolyte, and it's called an electrolyte because that solution will conduct electricity. Non-electrolytes, like molecules like methanol or alcohols or sucrose, when they dissolve in water, they don't break up into ions, they stay as a molecule, so those are known as non-electrolytes. So soluble ionic compounds tend to be electrolytes. Molecular compounds tend to be non-electrolytes because there's no charges, and in between you have weak electrolytes, weak acids, and weak bases. So when you have a strong electrolyte dissolved in water, the ions are completely dissolved, and the light bulb is strongly lit because it's basically conducting the full current through that solution. If you have a non-electrolyte like sugar, you're going to get no light in the light bulb because no current is allowed to pass through that solution. And when you have a pure substance like water, where there's no charges, also there will be no conducting going on. However, if you had a weak electrolyte, which isn't pictured in any of these, the light would go on, but it would be much dimmer than with the strong electrolyte. So this table gives you strong acids and strong bases. You need to know the 7 strong acids that are listed here, their names and their formulas. But those are one category of strong electrolytes, as are strong bases and soluble ionic salts. The solubility rules help us to sort out which compounds are going to dissolve in water and which compounds won't. So in this case, the first 4 rules that you see here deal with soluble compounds, So sulfates, chlorides, acetates, nitrates, and any compound that's made with a group 1A metal or ammonium are all soluble. There are some exceptions. You don't have to memorize the exceptions. You don't have to memorize all these rules. You do need to sort of memorize rule 1 and 2. The next 4 rules, 5 through 8, deal with the insoluble compounds. They are carbonates, phosphates, sulfides, and hydroxides, with barium hydroxide being an exception, a soluble hydroxide. Now, some textbooks will show calcium and strontium as being insoluble. Some textbooks show it as being soluble. It just depends on where you're looking. Not a big deal, but I just wanted to note that. And then remember, if any of these ions, these anions, are paired with a group 1A metal or ammonium, they are soluble. And that's really the one rule that you have to remember. This table is a different summary of the solubility rules. And then again, just remember this one statement that group 1A metal and ammonium and nitrate compounds are all soluble in water. Look back at the solubility rules if you need to, but make a decision about these 2 compounds in your summary sheet, sodium carbonate and lead sulfate, and indicate whether they are soluble or insoluble. Draw this picture or sketch this picture in your summary sheet. Pay attention to the numbers of each type of ion, and then explain or choose which compound is most accurately reflected by that picture. Is it potassium chloride dissolved in water, magnesium chloride dissolved in water, or potassium sulfate dissolved in water? And give just a quick explanation why. All right, so this first type of reaction that we're going to talk about is all of the reactions that we're going to talk about are metathesis reactions, but another way of thinking about them is exchange reactions. You will remember them from last year as being very similar to double replacement reactions. So the metathesis comes from the word in Greek that means to transpose, and they're called this because if you look at what happens, it seems like the partners, the ion partners, are just switching places in the product side of the equation. So metathesis reactions are exchange reactions, and we're going to look at 3 specific types of exchange reactions in this chapter. Precipitation reactions, where you have a solid ionic compound forming. Acid-base reactions, which are kind of speak for themselves. And oxidation-reduction reactions, in which there is a transfer of electrons between reactants. And many redox reactions are exchange reactions, however, not all of them are exchange reactions. So we will be looking at some of those in this chapter. So a precipitate, remember, is an insoluble solid compound that forms during a chemical reaction. So in order to predict whether precipitation reactions will occur, we need to know if there's a solid forming. So first we have to predict the products of an exchange reaction by exchanging the ions. Then we look at the products and we look at the solubility rules and we say, are any of those going to be solid or are they all going to be aqueous? If all the products are aqueous, then we say, nope, no reaction is going to happen because the ions basically stay separated, no change happens. If one of the products is insoluble, then we have a precipitate. And we start by writing the molecular equation. So remember, as you're thinking about these reactions, it's helpful to think about how the different substances actually exist in solution, whether they're ions, whether they're gases dissolved in water. And if we can understand how they exist in solution, that's going to help us determine what's happening during the reaction. So in this case, this reaction that we showed you earlier with silver nitrate and potassium chloride, switching partners or exchanging, forms silver chloride, which is the solid precipitate, plus potassium nitrate. So the first step is called a molecular equation because the formulas are written as though all of the compounds exist as molecules or whole units. Please don't confuse this. These are all ionic compounds. We're just calling it a molecular equation because we haven't broken them up yet. Okay, so it's still ionic compounds. This is just a type of equation that's called a molecular equation. Once we've got that written and balanced, then it's time to write the complete ionic equation in which all the electrolytes are broken up into their ions. So silver plus 1, nitrate minus 1, potassium plus 1, and chloride minus 1 are all written separately on the reactant side. On the product side, we have silver chloride written together because it's the solid precipitate. It's not broken up into its ions because it does not dissolve. And then we also have potassium nitrate written as potassium and nitrate ions separately. So remember, that's how they actually exist in solution when they're dissolved, so that's why we write them separately. Okay, once we've got the complete ionic equation written, we can cross out anything that occurs on both sides of the equation unchanged. So if we have nitrate ions on the left and we have nitrate ions on the right, we cross them out. Potassium as well. And what we're left with at that point is just what's called the net ionic equation. Only the species that have changed during the course of the reaction are left in the net ionic equation. And those species that didn't change or got crossed out are known as spectator ions. They don't actually participate in the reaction. They're just kind of hanging out and watching. Okay, so again, first write your balanced molecular equation. If you have strong electrolytes, dissociate them into their ions. Cross out anything that remains on both sides of the equation and write the net ionic equation out of what remains. So we're going to go through a few examples, 3 to be exact. I want you to write them all down in your notes. The first set of reactants is potassium bromide with magnesium sulfate. And remember, you need to first predict the products. So when we predict the products in this case, we get potassium sulfate with magnesium bromide, because again, we're just switching the partners. So this positive ion pairs up with the other negative ion, and so forth. The next thing you have to do is determine if the compounds are soluble or insoluble. In this case, both the potassium sulfate and the magnesium bromide are soluble compounds, which means they will be completely dissociated into their ions, as they were on the left side of the equation because they're both aqueous. So when that happens, there's no net reaction because basically nothing's changing. All of the ions are floating around on the left and all of the same ions are floating around on the right. So you have no reaction. The next example is an aqueous solution of sodium hydroxide and magnesium chloride. So the first step is to predict the products by the exchange of ions. So we're going to have sodium with chloride and magnesium with hydroxide. So we exchange the ions. These are our 2 products. Remember to write the correct formulas using charges. And then determine if one of them is a precipitate. In this case, the magnesium hydroxide is insoluble, and you figure that out by looking back at the solubility rules. Now we have an insoluble product, so we can write the complete molecular equation, and we have to balance it. Reactants on one side, products on the other, and the symbol for state is important at this point. Once we have the complete balanced molecular equation, we can write the ionic equation, keeping subscripts when they are appropriate to show the number of each type of ion. So sodium hydroxide, you can see, breaks up into 2 sodium ions and 2 hydroxide ions. Magnesium chloride as a reactant will break up into 1 magnesium ion and 2 chloride ions. So the subscript 2 in the formula becomes the coefficient 2 in the complete ionic equation. On the product side, we have 2 sodium chloride units, which break up into 2 sodium ions and 2 chloride ions. And we have 1 magnesium hydroxide unit, which is solid. It is not broken up because it is not dissolved in water. All right, so we've got all the ions written, so now we have to cross out anything that occurs on both sides of the equation. And what you're left with are the species that will represent the net ionic equation. 2 hydroxide ions, aqueous, plus 1 magnesium ion, aqueous, produces 1 unit of magnesium hydroxide, solid precipitate. So this next example, I'm going to tab through it very quickly, but I want you to pause the video here, and just try to do the solution yourself, work through the molecular equation, balance it, write the complete ionic equation and the net ionic equations. Okay, so first you predict the products, potassium chloride and calcium phosphate. Phosphates are insoluble, so there's your precipitate. Here's your molecular equation. Notice the coefficients that you need to balance it. It's a little bit trickier because of the phosphate -3 ion. The coefficients, remember, stay in the ionic equation, and here calcium phosphate is written as a unit because it is the precipitate. But the coefficient in front of chloride on the products on the reactant side is because we have a 3 coefficient and a 2 subscript in the compound calcium chloride. So keep in mind the numbers of each ion. Same thing here with the 6 potassium ions. Once you've got that, you can cross out anything that is the same on both sides of the equation. And then you've got the net ionic equation. So we're going to stop here for notes for today. Come in with your notes and we'll work through some examples in class.